All right, let's dive right into this explainer and completely demystify the complex, but honestly really fascinating setup of stateful traffic generation using Trex ASTF. If you're out there validating high-performance networks, you already know that generating traffic that actually mimics real-world behavior is just an absolute necessity. It's not optional. So today, we're going to break down the exact step-by-step playbook to achieve this using the Advanced Stateful traffic generator, specifically within an OVS DPDK environment. Here is our roadmap for today. First up, the stateful testing problem. Second, step-by-step ASTF architecture. Third, the OVS DPDK configuration guide. Next, essential contract best practices, avoiding common roadblocks. And finally, we'll wrap up with the high-performance payoff. Kicking things off with Section 1, the stateful testing problem. Let's start right at the root of the issue. You see, there's a massive fundamental difference between stateless and stateful testing. On one hand, you have stateless testing. Think traditional hardware benchmarking like RFC 2544. This is basically just blasting raw Layer 2 or Layer 3 packet streams at a device to find the maximum forwarding rate. And hey, it's great for measuring raw throughput, but it's completely blind to connection states. On the other hand, you have stateful testing. This is what you absolutely must use when validating NAT, stateful firewalls, load balancers, or OVS with Conntrack. These devices aren't just looking at isolated packets, they are tracking entire continuous sessions. The absolute bottom line here, you simply cannot validate a stateful firewall or an OVS DPDK Conntrack setup with raw packet blasts. It just doesn't work. To properly test environments that track connection states, your traffic generator needs to speak the full, intricate language of client-server handshakes. We're talking the real SYN, the SYNAC, the entire data exchange, and the final thin teardown. If you just blind fire packets at a stateful device, it's going to view them as invalid and drop them immediately, and your test fails before it even really begins. Moving right along to Section 2, step-by-step ASTF architecture. So how do we actually fix this? Enter Trex ASTF. This solves the problem so elegantly, it isn't just sending packets out into the void hoping for the best. It actually runs a full, legitimate TCP and UDP stack inside itself. It acts as the initiating client on one port and the responding server on the paired port. It handles the whole connection lifecycle internally, and that is a massive advantage because it completely eliminates the need to stand up separate, external servers just to sync your test traffic. It's an all-in-one solution. And the beauty of this architecture is how well it scales, step by step. Step 1 is the absolute simplest approach, a direct bare metal connection where a Trex dual-port NIC connects straight to the device under test. Easy, right? Step 2 introduces a bit more complexity by routing that single port pair through an OVS DPDK bridge and into a VM using MAC forwarding. And finally, Step 3 is the full enterprise scale. This is a multi-port pair setup using 4 paired ports to distribute massive amounts of traffic across completely isolated IP ranges. Okay, let's roll up our sleeves. Section 3, the OVS DPDK configuration guide. Look, before you even think about hitting run on a test, there are 4 absolute prerequisites. Seriously, you cannot skip these. First, you must increase your contract table size. Second, you have to configure your OVS zone timeout policies. Third, explicitly tune your kernel contract timeouts. And fourth, distribute your traffic by configuring multiple physical port RX queues. If you don't do that last one, you're going to bottleneck a single CPU core, and your performance will completely tank. Now, sizing that contract table, it is heavily dictated by your specific traffic profile. Let's say you're blasting short-lived TCP or a mix of TCP and UDP traffic. Your steady-state connection count is going to absolutely skyrocket. You're going to need a contract max size of 2 million or more. But if you're testing long-lived TCP, where connections establish and just sit there quietly, you can get away with a much smaller table, somewhere around 500,000. Sizing this correctly is absolutely crucial to prevent your flow table from just silently dropping your test traffic. Which brings us nicely to Section 4, Essential Contract Best Practices. Okay, here is a massive hidden roadblock that trips up so many people. Why on earth would you tune your host's kernel timeout to 120 seconds instead of just matching the 30-second OVS data path? I mean, it seems perfectly logical to match them, right? Keep everything synced up, but doing that actually triggers a massive hidden issue. The secret here is that you have to draw a hard line between your OVS data path and your host kernel. Let's say you set the kernel timeout to 30 seconds. What happens during a heavy 60-second high-stress trial? Well, your vital infrastructure connections, things like the Redis heartbeat your testing controller relies on or your SSH sessions, they just sit idle. The kernel thinks they're dead and expires them.
Then, when a heartbeat response finally tries to make its way back, the host drops it as an untracked packet. Your whole test aborts completely with a catastrophic RC=5 timeout error. It's basically a fatal crash. Keeping that kernel timeout at a relaxed 120 seconds keeps your management tools alive while the OVS data path does the heavy lifting.
Next up is a parameter called ASTF flush on pass, and let me tell you, this parameter is pure magic. When you test stateful firewalls or OVS Conntrack, if a trial passes, the default behavior is that traffic just keeps running. But that means your next trial inherits all the accumulated stale contract entries from the previous one. This stale state acts like a ghost in the machine, causing massive retransmit spikes and failing your next trial artificially. By enabling flush on pass, you force a hard stop. You wait for a graceful TCP teardown, and then you execute a script to entirely flush the OVS data path contract table. It guarantees true 100% per trial isolation.
All right, Section 5, Avoiding Common Roadblocks.
So by default, Trex shares its full pool of IP addresses across all of its data plane processing cores. The problem with this? Multiple cores can easily accidentally generate packets using the exact same source IP at the exact same time. This creates duplicate 5 tuples, and that leads to severe retransmit confusion and massive contract churn. When you explicitly change this to distribute your IPs using the seek or sequential mode, you're essentially giving each core its own exclusive private subset of IPs. You completely eliminate cross-core contention, which drops your retransmit rates off a cliff and dramatically improves your latency.
Let me give you 2 quick fixes that will literally save you hours of tearing your hair out debugging. First, if you're doing OVS DPDK testing with a VM in MAC forwarding mode, you're inevitably going to see CWF errors. That stands for Client Packet Without Flow. Don't panic. This isn't actually a failure. The return packets are just arriving on the paired port due to the nature of how MAC forwarding works. Just tell Trex to ignore that specific error. Second, if you're testing a realistic mixed profile, say 99% TCP and just 1% UDP, you need to relax the UDP drop threshold to something like 20%. Why? Because UDP has no graceful teardown mechanism and is hypersensitive to device stress. Relaxing this ensures your test is graded on the health of your primary TCP traffic rather than failing early just because of a few minor UDP drops.
Finally, we made it to Section 6, the high-performance payoff.
86,255. Take a second to appreciate that. That is the number of validated, perfectly stable, non-drop rate connections per second achieved for TCP traffic on an OVS DPDK setup. It is a phenomenal result, and the only way you hit numbers like this is by combining that persistent in-process mode, utilizing flush on pass for guaranteed clean states, and employing sequential IP distribution to completely sidestep core collisions.
And the best part? This methodology isn't just fast, it's incredibly efficient. Because you're controlling for all those stale contract states, your binary searches won't jump around and oscillate wildly. They converge cleanly and monotonically in just 15 trials. That means 0 false positive collapse. You never have that nightmare scenario where the search passes a super high rate, only to mysteriously fail at a much lower one just because of lingering flow table garbage. Which brings us to our final thought for today. I want you to take a hard, honest look at your testing pipeline right now. Is your testing environment truly simulating complex, real-world stateful traffic, or are you just settling for raw packet blasts? Because if you're tasked with testing stateful infrastructure, relying on stateless blasts is leaving you entirely blind to how your network will actually perform in the real world. Hopefully, this explainer has given you the exact playbook you need to upgrade your testing infrastructure and confidently validate even the toughest stateful environments out there. Keep learning, keep testing, and I'll catch you on the next explainer.